Welcome to This Explainer. Today, we're going to tackle what is arguably the ultimate mystery of the cosmos. What exactly preceded the Big Bang? It's a question that completely bends the mind, and we're going to look at the absolute cutting-edge physics attempting to answer it. Okay, let's dive into this.
So, what happened before the Big Bang? I mean, it's the most natural question in the world to ask, right? When you think about the universe starting from this incredibly hot, dense state, your brain immediately wants to know, well, what was there before that? But historically, if you asked a theoretical physicist this, they'd probably just slap the question down. They'd tell you the premise itself is fundamentally flawed.
Theoretical physicist Sean Carroll perfectly summarizes this conundrum. He says, asking what's before the Big Bang is like asking what is north of the North Pole. The traditional view, which is heavily rooted in Einstein's general relativity, is that space and time are one single dynamic fabric, and that fabric literally began at the Big Bang singularity. Under that model, there just is no before. But here's what's really thrilling. Modern physics isn't stopping there. Because general relativity doesn't account for quantum mechanics, new, completely mind-bending theories are challenging this old assumption and attempting to peek right past that singularity.
So here's our roadmap for today. First, before the Big Bang. Second, the cyclic universe theory. Third, cosmic inflation explained. Fourth, the fractal multiverse. And finally, number 5, the anthropic principle.
Section 1. Before the Big Bang.
To understand how we might look prior to our universe's origin, we first have to understand exactly where our current physics hits a brick wall. If we define the Big Bang as the extremely hot, dense, rapidly expanding universe described by Einstein's equations, well, our picture is actually incredibly solid down to about a trillionth of a second after the beginning of time. We can even make highly educated scientific guesses down to 10 to the negative 30th of a second. But as we push all the way back to 13.8 billion years ago, the exact moment of the Big Bang itself, the math just breaks down into an infinite singularity where density and curvature become infinitely big. To push past this limit, scientists are having to propose entirely new frameworks.
Section 2. The cyclic universe theory. This brings us to our first major competing paradigm, championed by the brilliant Oxford mathematical physicist Roger Penrose. He calls this theory Conformal cyclic cosmology, or CCC for short. The core idea here posits that our universe is just one stage in a potentially infinite cycle of cosmic extinction and rebirth. Penrose calls these stages aeons. Imagine an infinitely old, completely empty universe in the far, far future. According to CCC, as matter gets sucked into black holes and those supermassive black holes eventually evaporate, all particles lose their mass. And at this point, the universe literally loses track of its own size, mathematically matching up with an infinitely small, ultra-smooth point, setting the perfect stage for a brand new Big Bang.
But how could we possibly test something from a previous universe? Well, Penrose proposes we look for what he calls Hawking points. If a supermassive black hole evaporated in the previous eon, it would leave behind concentrated spots of massive energy. Penrose calculates that in our current eon, these ancient emissions would have stretched as the early universe expanded, forming these circular patches in our cosmic sky, with a diameter about 5 times that of the full moon.
So, how does this build into an actual hunt for data? Penrose, along with researchers Daniel N. and Christoph Miesner, claim to have found evidence of these Hawking points in the actual cosmic microwave background, the CMB, using data from the European Space Agency's Planck satellite. They looked at real CMB data and found anomalous hotspots with massive temperature variations of about 3 times 10 to the negative 4 Kelvin. When they ran 1,000 standard inflation simulations, not a single simulated map had temperature gradients as high as what they observed in the real cosmos. They argue this disparity is a strong signature from a previous aeon.
However, in the spirit of objective science, we absolutely must look at the heavy community skepticism this claim has faced. Cosmologists like James Zibin and Douglas Scott remain largely unconvinced. They point out that these anomalies were only found in 2 out of 40 specific tests, focusing on different spot sizes and boundary regions. This suggests the researchers failed to account for the look elsewhere effect, meaning if you look at enough random spots in the data, you're statistically bound to find something that looks anomalous. Because of this, they argue the data might simply be a statistical fluke. Some peers have even described the paper as muddled and hard to follow. So the search for cyclic signatures remains a fiercely debated and highly active area of physics.
Section 3. Cosmic inflation explained. Now, what's really interesting about this slide is how we pivot to the second theoretical path. This is widely accepted by many cosmologists as the best description of the time before the Big Bang. But as you'll see, it's incredibly strange.
Here, we are introduced to the true bang in the Big Bang. Instead of a singular point exploding, physicists propose that the early universe was driven by something called the inflaton field. This is a quantum scalar field, described by a single number everywhere in space, kinda similar to the famous Higgs field, that contained a massive amount of vacuum energy. It was the energy trapped in this field that drove a brief, exceptionally intense period of exponential expansion of space itself.
To understand how this works, let's break down the mechanics of slow-roll inflation developed by André Linde, Andreas Albrechts, and Paul Steinhardt. Think of it like this. Imagine a ball resting on a high-energy, weakly sloping plateau. That's step 1, the false vacuum plateau. Then the field slowly rolls down this energy slope. That's step 2, powering the exponential expansion of space while keeping the energy density nearly constant. Finally, in step 3, the field hits the deeper valley at the bottom. The expansion stops smoothly, and the field releases all that pent-up energy as hot, dense matter. This process, called reheating, is exactly what creates the expanding, hot, dense universe that we know and love in our standard Big Bang model.
Section 4. The fractal multiverse. Okay, so we just saw how the slow roll process smoothly ends to create our universe. But we've got to ask a critical question here. What happens if this rolling process doesn't stop everywhere at the exact same time? The answer lies in the intrinsic randomness of the quantum world. As the inflaton field rolls down the hill, quantum fluctuations cause the field strength to jitter. Most of the time, the field decays and inflation ends, but occasionally, a rare, strong quantum fluctuation will actually push the field back up the energy slope in a certain region. Because inflation causes exponential expansion, that tiny patch of space where the field was pushed up will rapidly outgrow its surroundings. The astonishing conclusion: quantum fluctuations ensure the exponential expansion of space never completely stops. This mind-blowing concept is known as eternal inflation. Because inflation never truly stops globally, the universe becomes a mutating, eternally growing fractal. It's a vast expanse of inflating space, peppered with bubble universes where inflation has stopped. What's absolutely wild here is that the energy jumps near the Planck density are so violent that each of these new bubble universes could have completely different laws of low-energy physics, or even a different number of dimensions. They effectively forget the genetic code or color of their parent universe.
And this brilliantly illustrates the sheer scale of this boiling, self-reproducing multiverse. Once a bubble universe forms and its internal inflation stops, the space between it and the next bubble just continues expanding exponentially. This means the tubes connecting these universes stretch and eventually evaporate via Hawking radiation. The bubbles literally pinch off from one another, completely losing their causal connection. So our observable universe is just one of these isolated bubbles inside an immortal, eternally reproducing cosmic fractal.
Section 5. The anthropic principle. Now you might be wondering why this mind-bending theory of a fractal multiverse matters to us. Well, surprisingly, it actually solves one of the greatest mysteries about our own existence. 10 to the power of 500. In the context of string theory, physicists estimate that this is the staggering number of possible stable or metastable vacua. Basically, the different types of physics and parameters a bubble universe could possess in the cosmological landscape. With eternal inflation spawning infinite bubbles, all 10 to the 500 possibilities are realized somewhere out there in the greater multiverse.
And this is highly relevant because our universe appears suspiciously perfectly tuned for us to exist. We live in a four-dimensional space-time, which happens to be stable for planetary and atomic systems. We have an exact proton-to-neutron mass ratio and specific electron charges that allow chemistry to happen. We also have a minuscule but non-zero cosmological constant. That's the vacuum energy. If that vacuum energy were just slightly larger, the universe would have expanded so violently that galaxies, stars, and organic life could never have formed.
So the crucial point is this. We observe a seemingly perfect, finely tuned universe simply because we could only ever exist in a bubble where the physical laws allow for our existence. This is called the anthropic principle. We aren't incredibly lucky to have rolled the exact right laws of physics on the first try. Rather, the multiverse tries every possible combination of physical laws infinitely, and we just happen to live in one of the specific bubbles that supports intelligent life.
Which leaves us with this final, profound question to consider. If our universe is just one temporary bubble in an eternally expanding fractal cosmic landscape, what does that mean for our place in the multiverse?
Are we truly alone in our specific physical reality? Or are there countless other bubbles out there in the vast string theory landscape harboring totally different kinds of life? It really forces us to ponder whether our 13.8 billion-year-old Big Bang was just a tiny, fleeting spark in an immortal, unending cosmic fire. Thank you for joining me for this explainer. Keep wondering and keep looking up.